Okay, so if you have any questions from the homework, feel free to ask me after class, okay? Right now, I want to begin with this section. So this is the last section that we need for the exam. So if everything goes well, we should finish between today and Wednesday, and then next week will be the next exam, okay? On Wednesday, I will give you more information on what to prepare and so on, but basically, as usual, just do the homework, okay? Make sure you can do the homework and review all the examples that we do in class, because not every, there are different type of topics. There are some topics that are good to be tested using a computer, and that's what you see in the homework, but there are some questions that just cannot be tested using a computer, and those are the type of examples that typically we do in class, okay? So you need to see both, because in the exam, as you saw from the first time, the first one, both could show up, okay? Not could, they will show up. So don't neglect the notes. Okay, anyways, this is the last section. Let's talk about it. This is the notion of cardinality. We kind of introduce this idea when we're talking about finite sets. So when we're talking about sets, and then for finite set, we say cardinality is just the number of elements of the set. But what if the set is infinite? Okay, what does it mean to say number of elements? Okay, for example, the natural numbers and the integers, do they have the same cardinality? They definitely don't have the same number of elements, right? But do they have the same cardinality? Because the natural number is a proper subset of the integers. How about the integers and the rationals? The integers is a proper subset of the rationals, okay? But do they have the same cardinality? How about the reals, the real numbers? So we need to do some exploration here. But of course, so when the sets are finite, it's pretty straightforward. But when the sets are infinite, how do we talk about cardinality? So let me write a definition. So how do you decide that two sets have the same cardinality? Basically, we're going to be using functions for this, okay? So two sets have the same cardinality if there is a bijection between them, okay? So as our first definition, so number one, so let A and B be two sets, then we say that A and B have the same cardinality if there is a bijection between them. If there is a bijection between them. Okay? So in other words, if we have a function from A to B, or from B to A, it doesn't matter, okay? Such that f is both injective, so one-to-one and on, okay? Injective and surjective. Okay, that's what it means for two sets to have the same cardinality. And then we have a special notation for cardinality, as we saw before. We use the absolute value symbol. Okay, and in this case, we write that the cardinality of A equals the cardinality of B. Okay, and some places you will see that they also write this, like CRD, right? For cardinality, you could also see that notation, or you could also see n of A, or the number symbol of A. All of that are different notations, but I will be using the absolute value symbol. Okay, this is notation for cardinality. Notation. Okay, so I'll be using this one. All right, any questions of what it means for two sets to have the same cardinality? It just means that there is a bijection between them, okay? That you can find a bijection between them. And then number two, because we're using, this notation, there is a notion of saying less than or equal to, or strictly less than, okay? And basically, when you say less than or equal to, what you're saying is that the cardinality of A is less than or equal to the cardinality of B. What does it mean? It means that there is an injective function from A to B. Okay? So, if there is an injective function f from from A to B, then we say that the cardinality of A is less than or equal to the cardinality of B. And then, of course, we write cardinality of A less than or equal to cardinality of B. But understand that when this notation is used and these guys are sets, what we're saying, this is just a way of saying there is an injective function from A to B. Okay? There is a one-to-one function from A to B. That's what this means. There is a one-to-one function from A to B. This means there is a bijection from A to B. Okay? Now, if it turns out that there is no bijection, in other words, if it turns out that the cardinalities are not equal, it means this is strictly less than B, and so we write less than. So if the cardinality of A is different than cardinality of B, and still in the same definition, then we write cardinality of A is less than cardinality of B. In other words, what we're saying is that there is an injective function from A to B, but that there is no injective function from A to B that's also surjective. That's basically what we're saying. You cannot find a bijection between them. Okay? All right. Any questions on this? So again, we need to use functions when we talk about, when we're dealing with infinite sets, this is the language to use, okay? Functions. Now, I gave you a theorem last time, and I'll give you the name. Let me remind you of this theorem, because, in these situations, it's helpful. I'm not sure how to pronounce it. So, the Schroeder-Bernstein theorem. That says, okay, sometimes it's actually difficult to come up with a bijection between two sets, but it's way easier, as we saw last time in an example, to actually find an injective function from one set from A to B, and then another injective function from B to A. Okay? If you can do that, then it means that there is a bijection. And now it makes sense because, so before I write the theorem, if you think about numbers, what happens if you say that absolute value of A less than or equal than absolute value of B, and absolute value of B less than or equal than absolute value of A? What can you conclude if you see this, at least when you're thinking about numbers? Imagine that these are numbers, okay? This is a number and this is a number. So what can you conclude here? They're the same, right? So if this happens, then that means these two things are equal. Well, when it comes to sets, the same thing happens, and that's what this theorem says. Here, what are we saying? There is a one-to-one. There is an injective function from A to B, and if you can find an injective function from B to A, then you can find a bijection between them, or there is a bijection between them. Whether you can find it or not, that's a different story. We mentioned that theorem last time, so this theorem is very helpful here. If you want to argue that two sets have the same cardinality, you need to produce a bijection or show that a bijection exists. Sometimes this is hard. So what you can do is find a one-to-one function from A to B, and then a one-to-one function from B to A, and then you're done. You can call this theorem. Okay. So the theorem says if there is an injective function from A to B. Actually, I'm going to use our notation. We already have the notation. So if the cardinality of A is less than or equal, let me say this as sets. So let A and B be two sets. Then the statement is if the cardinality of A is less than or equal than B, then the cardinality of B and the cardinality of B is less than or equal than the cardinality of A, then they have the same cardinality. Now understand that with this notation, because I'm saying that A and B are sets, this is just a shorthand for saying there is an injective function from A to B. This is a shorthand for saying there is an injective function from B to A. And this is a shorthand for saying there is a bijection from A to B. Or from B to A, doesn't really matter. Okay? So understand that. We already defined that above. Are we okay with this? All right. Now, let's see in practice how we identify these things. So let's do an example. So, for example, show that the cardinality of the positive integers is the same as the cardinality of the odd positive integers. Okay? So let me fix the notation here. So every time that we have a set, a well-established set, if I put a plus here, I just mean the elements in this set that are positive. Okay? So this is elements x that are integers such that x is greater than 0. You understand this? And if I put a minus, it means the negatives. Okay? All right. So the problem here is to show that the cardinality of the positive integers. So if we enumerate this, what is this? Let's list this in cluster notation. What are the elements here? 1, 2, 3, 4, 5, and so on. Talking about this. Okay. Now, what is this one? This is 1, 3, 5, 7, etc. So, if you purely are looking at size, at number, amount of numbers, which one has more elements? Amount of elements, which one has more elements? This one, right? Because this one has 2, 4, and so on top of all of these guys. You understand this? So this is a proper subset of this. However, we're saying they have the same cardinality. This is to let you know that cardinality is no longer the same as amount of elements. Okay? But this happens when we're dealing with infinite sets. For finite set, then yes, of course, same cardinality means same amount of elements. But for infinite sets, not necessary. All we have to do is find a one-to-one correspondence between the two. So a bijection. Okay? All right. So how do we do this? The solution. How do we do this? Well, one way to do it is construct the function. Okay? Construct the function and then argue that this function is a bijection, and you're done. So let's see. So I'm gonna put here option 1 because then I'm gonna show you an option 2. Okay? Oops. Option 1. Construct the bijection. Find the bijection. All right. So in this case, we can easily do it because we have a definition for the odd positive integer. What's the definition of an odd number? 2n plus 1. Right there, you have your bijection. Okay? Our job is to show that it is actually a bijection. So let's say f is a function that goes from C plus to the set of odd integers, odd positive integers. And what it does is it takes an integer and then it sends it to. So let's see. I'll say 2n minus 1. I'm not gonna say 2n plus 1. And the reason why, because if you put 2n plus 1 here, then what will be the first value of this function? It will be 3. So you're gonna be skipping 1. Understand this? So if you put plus 1, you're not gonna get 1 in your range. Okay, so the image is not gonna contain 1, so it's not gonna be on. You understand this? But if you do 2n minus 1, which is equivalent, now when n is equal to 1 here, we are gonna capture 1 as an output. Do you understand this? Okay. For example, if I would have said the naturals, or in other words, the greater than or equal to 0, then you can do plus 1 because you start at 0. And then you're going to capture the 1. Okay, so just be careful when you do your formula. Make sure that you capture everything that you need. Okay. Anyways, here, because the first element is a 1, then I need to have 2n minus. And because it's an increasing formula, then the bigger n gets, the bigger this number we get. So we're not going to get the 1 anymore if I put a plus 1 here. And it wouldn't be odd. Okay, so in other words, the formula is f of n equals 2n minus 1. Okay? And now all we have to do is to argue that these two sets have the same cardinality. We need to show that this is a bijection, right? How do we show that this is a bijection? So we need to prove that it's injective, and we need to prove that it's surjective, right? So claim F is a bijection. All right, so let's do it. So first, we show that F is injective. How do we prove that a function is injective?
If f of n is equal to f of m, then n equals m.
Very good. So, in other words, let's assume that we have two inputs that produce the same output, right? So let n and m be two numbers, two positive integers, such that f of n equals f of m. Everybody okay with this? Remember, these guys have to be inputs, so they have to come from the positive integers. Now, our job is to argue that n must be equal to m. Okay? Well, in this case, it's straightforward, right? We have a formula, just put it and solve. So this means then that 2n minus 1 must be equal to 2m minus 1, right? Subtract ones, so you get that 2n equals to m, divided by 2, we get n equals m. So therefore, f is injective. Everybody okay with this? All right, so we got that. Now, what else do we need to argue? That it is surjective. Now, what does it mean that it's surjective? So f is surjective. What do we need to prove?
F of n is equal to n.
Yeah, but tell me what are n and what are m. What do we need to prove? What does it mean to be surjective?
Every of the color there is an element of the domain that equals f of that says that every function of the domain equals the color.
So, in simpler words, what does it mean to be surjective? The image of the function has to be the entire codomain. In other words, every element in the codomain has a pre-image. Okay? So we need to show that every possible odd positive integer can be obtained by using this formula. That's what we need to show. Do you understand this? In other words, for a given positive integer, for an arbitrary positive integer, we need to construct odd positive integer, we need to construct a positive integer, so that when I plug it into this formula, it gives me that given number that we started. Okay? That's what it means to be surjective. That every element here can be written as this, 2n minus 1. Okay? That's basically what we need to argue. How do we do that? Well, start with an arbitrary element in the codomain and then construct a pre-image. Okay? If we manage to do that, then we're good to go. So let m be any positive odd integer. Okay? So let m be any positive odd integer. Now I just need to show that there exists an integer n, so when I plug it into the function, I get this n, right? So how do we do this? What do we need to do at this point? So we do our little corner calculation. We do this where nobody sees it. So what do we want? We want an n, so that when I plug in, gives me m, right? Well, let's figure out what this n has to be. This is 2m minus 1. So n is going to be m plus 1 divided by 2. Do you understand this? Okay, so now nobody sees that. You do that in the corner. Now come back and we continue with our proof. Let n be any positive integer, odd integer. Okay, then consider n to be this number, n plus 1 over 2. Nobody can stop me from doing this. You give me an integer, I do plus 1 divided by 2. Okay, you can do that. Now the question is this what's supposed to be? In other words, is this an integer? We need to argue this. Is this an integer?
Not every time.
Why not?
Because sometimes you'll get a rational number.
look at the problem. So not every time is an integer, but in our case, is this an integer? So what's m? It's odd. What happens when you do plus 1 to an odd number? You get even. So when you divide by 2, you're good. You understand this? This only makes sense because m is odd. If m is even, then you cannot play this game. You understand this? So then consider this number. Now the point is that this is a positive integer since m is odd, and so m plus 1 is even. So when you divide by 2, you're good. Everybody okay with this? All right. So given an element in the codomain, we constructed an element in the domain. Now our job is to show that when I plug in this n, I get m, and we're good. Okay. Now all you do is plug in and compute. We know it's gonna work. That's the reason why we did this little job here, right? It's basically just doing this backwards. We know it's gonna work. So and so m plus 1 is even. So then f of n equals 2m minus 1, which is 2 times m plus 1 over 2 minus 1, 2's cancel, and you get m plus 1 minus 1, which is m. Okay? So we just show that for every m, we can find an n in the integer, so that when you plug in n into the function, you get your m. That's what it means to be surjective. Okay? Because m is important. It's any. It's arbitrary. Okay? So f is surjective. And we just proved that it is both injective and surjective. Therefore, f is a bijection. Questions? And since we know that f is a bijection, then what can we conclude about these two sets? They have the same cardinality. Okay? So, the cardinality of the positive integers is the same as the cardinality of the odd positive integers. Okay. Questions?
So this method is mostly for infinite sets.
Yeah, I mean, when the sets are finite, you don't really need to construct the function. You just see, look, this has 20 elements, this has 20 elements, so same cardinality, right? When the sets are finite, you can count the elements. The thing is that when the sets are infinite, what do you mean by counting the elements, right? Look at this. This guy has the odd positive integers. Certainly, this has less elements than the one on the left, right? This is a proper subset of this one. But nevertheless, that's the cardinality because there's a one-to-one correspondence. Basically, here we're saying every element here can be paired to an element here in a unique way. So that's what it means to have same cardinality, which in the finite case is equivalent to say same amount of elements. But in the infinite case, that doesn't hold anymore. But the bijection is universal. It's what makes sense. That's why we needed to study functions first. Okay, so we could do this. Any questions? Now, I wrote here option 1. That means there's a second option for this, and the second option is way easier. It's just that it's a little bit informal, but it's okay, and you will see why. Okay? In other words, here, what do? We explicitly constructed the function. Okay? I gave you the function from C plus to this guy, so that is a bijection, and then nobody can argue. Okay? Now, this is, in general, this is hard to actually come up with the formula. This case was easy because the sets are straightforward to deal with. Okay? But if I put here the rationals, this is not that straightforward to find the bijection from the integers to the rational, if there is any. You're going to answer that question soon. Okay? So, are there other strategies to argue that, that there is a bijection between two sets? I gave you one here. You can just try to find two one-to-one functions. Or, in this case, this set here is very special. What is this set? What is this set? C plus. So what is it? 1, 2, 3, 4, 5, etc. What do you use those numbers for? To count. In other words, if I give you a list, then you can count. This is the first guy, this is the second guy, this is the third guy, so on. Do you understand this? So if I give you a list, I'm implicitly giving you a function from C plus to the set to that set that I'm listing the elements. Because when I give you the list, I'm just saying one, the image of one is the first element. The image of two is the second element, and so on and so forth. Do you understand what I'm saying? So I'm telling you element by element. So if you are able to list every element in your set, then you know that there's a one-to-one correspondence with the positive integers. So an alternative way is, if you want to show that a set has the same cardinality as C plus, you will construct a function or produce a list of the elements in that set. Now here a list has to have a beginning. You need to tell me how to start the list. Okay? If you manage to do that, then you're good to go. In other words, option number 2, did I use red? No. So option number 2, and typically whenever possible I will be doing this. Okay, it's a little bit more informal because you are giving an implicit definition, but it's fine. That also works. Okay, so the idea here is we may implicitly define our bijection by showing or producing a list of all the elements in the old set, which is the set of all integers. Positive or integers. Okay, so this is an alternative. If you don't want to come up with a concrete formula, this is very special because we're comparing with C+. Okay, this is because we're comparing with C+. Then what you can do alternatively is try to list the elements. So indeed, I can list the elements. So the positive integers, positive odd integers, they can be listed. So these are 1, 3, 5, 7, 9, and so on. So what's happening here is that by me giving you this list, I'm implicitly already giving you the bijection. What bijection am I giving you? Well, down here, you can think of having the set C+, and then I'm just saying, okay, look, the first element is going to be the image of 1. The second element in the list is going to be the image of 2. The third element is going to be the image of 3, and so on and so forth. Do you understand this? So by showing that the elements of your set can be listed, you are implicitly telling me that there is a one-to-one correspondence with the positive integers. Okay? So this is a bijection. So this right here is a bijection. It's a one-to-one correspondence, which is exactly what a bijection is. Okay? So the cardinality of C plus is the same as the cardinality of the positive integers, of the odd positive integers. Okay, so the moral of the story here is that if you're wondering whether a set has a cardinality of the positive integers, what you can do is, instead of producing a function that typically is not that easy, try to see if the elements can be listed. If you manage to do that, then you're good to go. Now understand that when we say a list, the list has to have a beginning. You have to have a reasonable way of having a beginning, and you have to make sure that your list produces every single element in your set, that you're not skipping anybody. Okay? Here it's clear that we're not skipping anybody, right? If we keep on going this way, we're basically just adding plus 2. Start with 1 and just do plus 2, plus 2, plus 2, plus 2, and then you're gonna cover. And basically, this is exactly the bijection that we produced at the beginning, by the way. Okay? The formula that we use, the 2n minus 1, that's exactly what's happening here, from here to here. we're doing 2n minus 1. So that is consistent every time, we're doing 2n minus 1. Okay? But you don't need to come up with the formula itself if you manage to list the elements. Now, you need to convince your audience that your list contains everybody in your set. That's the only thing that you need to argue. Now, here it's clear. There is no need to argue anything for that. But when the set is more complicated, you may have to do some arguing. Okay. Any questions? Do you understand this? All right. So let me actually another example. How about, to use the same idea, let's show that the cardinality of the positive integers is also the same as the cardinality of the odd integers. So I'm basically doing the one above, but I'm also throwing in the negatives. Above, we only dealt with positives. Okay? Now I'm throwing in the negatives. So by C odd, and I mean, so when I say C odd here, what I mean is, it has 1, 3, 5, 7, and so on. But it also has -1, -3, -5, and so on. Okay? So it's the ones above together with their negatives. And still, notice that we throw in an extra infinite set, and still the cardinality is not going to change. It's the same as the cardinality of the positive integers. How can we do this quickly? So here you think a little bit harder. You could produce a function as well, maybe, but you have to think harder. Okay? However, there is no need to break our head with this. If we manage to show a list of this set, we're good to go. Right? Now remember, what I did here, it looks like a list, but this is not really a list. Why is this not a list? It doesn't have a beginning. It just keeps going all the way to negative infinity. To give me a list, you need to give me, I need to know who is the first guy, who is the second guy, who is the third guy. Here, I don't know. Okay? So this is not good. What can we do? Is there another way to list? Is there a way to produce a list?
Can you create like two subsets of, one of the negative odd integers, one of the positive, and show that for each?
Well, let's see. So that's more complicated. So there will be a theorem later that we're gonna discuss that says that if you have a set that has the same cardinality of the integers and another set with the same cardinality, then the union still have the same cardinality. But that'll come later. So there is a simpler way to do this. In fact, the way we're gonna prove that is exactly what we're gonna do here. So let's just start getting used to it. What's another way to do it? Well, I mean, we need to have a list with a beginning, right? Let's begin our list. Now, I cannot go all the way, start with 1 and go all the way, and then begin with the negatives, for example, right? Because I will never stop. So I will actually never get to the -1. You understand this? You need to convince me that I will get to -1, I will get to -3, I will get to -5, and so on all the time. So instead of doing the first thing and then starting with the other one, alternate 1 and 1. Okay? So we can do 1, -1, 2, -2, 3, -3, and so on. Do you agree that if I do this, every single integer is going to be, every single odd integer will be in this list? Yes or no? Do you understand this? So we produce a list, and it has a starting point. So this is now a valid list. Now, you don't have to give me this list. You could give me another list. You could give me 1, 2, 3, then -1, -2, -3. Then 4, 5, 6, -4, -5, -6. And so on. You can do whatever you want, as long as your list contains everybody in the set. Okay? So now, this right here is a list. So this is a list of all the elements. This is important, of all the elements of the odd integers. Therefore, the cardinality of the odd integers then is the same as the cardinality of the positive. Very simple. and you don't have to actually build the function then, because once you build the function, then you need to argue that it's a bijection. You need to prove one-to-one, you need to prove onto, and all of that business. Okay? You can get away by producing a list. Now, this is only special for this guy. Okay? Now, you're gonna see why I'm making a big deal about this guy, because this guy is very special. Okay? So, we're gonna see that pretty soon. Anyways, questions about this? No, I don't know why 2 is there. It should be 3 and this should be 5. Okay, good. So 3, -3. 5, -5. Yeah, good. So I'm basically doing this. This guy, this guy, this guy, this guy. So, we're moving this way at once in the list. That's basically what's happening. Okay? This, and so on. Eventually, you're gonna get to whatever you wanna get. Okay? Every odd integer will be in this list. Good. All right. Questions? No questions? Okay. So before we do another example, let me then make a definition. Sets that have this behavior, they have a special name. We call them countable. Okay? A set is said to be countable if 2 things: if finite, or the elements can be listed. In other words, if it has the same cardinality as the positive integers. Okay? So let me write that down. Therefore, the positive integers are special, so we have a special symbol for the cardinality of the positive integers. Okay? So definition, we write for the cardinality of the positive integers, we write this symbol. Okay? And we call this aleph null. So this is aleph null. And what this symbol represents is just the cardinality of the positive integers. Now, there's a reason for this, because this is the first type of infinity that we have. If you will, it's the nicest type of infinity. But then there are other types of infinity that, in a sense, are bigger than this one. Then, there are aleph 1, aleph 2, aleph 3, and then you have aleph. And this keeps going, and it goes crazy. Okay? Set theory is not easy, okay? This is very complicated. We're just scratching the surface, the top. Anyways, and this is a very special cardinality, so we have a symbol for it. It's called aleph null. And then anybody that has the same cardinality as C+, we call it countable. Okay? Or if it's finite. So let me write it down. The definition. A set A. Okay, let me just say a set is countable, is said to be countable if it is finite, or it has the same cardinality as C+. Okay? So in other words, A is countable if A is finite. Oh, let me just say here, so if A is finite, it's countable, and then if A is infinite, then it is countable if its cardinality is aleph null. Okay? In other words, if an infinite set is going to be countable if its cardinality is the same as the cardinality of the positive integers. Okay? And remember, the symbol is reserved for the cardinality of the positive integers. So, to continue this paragraph, if a set is not countable, we say is uncountable. Okay? If a set is not countable, so not countable means, of course, it's not finite, and also that you cannot find a bijection between your set and C+. If you cannot do that, then we say the set is uncountable. If a set is not countable, then it is uncountable. And then, of course, this only happens for infinite sets. So sometimes people will say uncountably infinite. Okay? But when you say uncountable, it already implies that it's infinity. But sometimes we say uncountably infinite. Okay? Because being finite automatically makes you countable. Okay? To fail, to be countable means that you are a particular an infinite set and that your elements cannot be listed. That's what it means. Okay? So, in summary, how do you know whether a set is countable or not? If the elements can be listed by using what we just did before. So, remark, an infinite set A, or any set, if even it's finite. So, a set is countable. If it's finite, that just means that the list stops, right? If it's infinite, the list keeps going without stopping. So, a set is countable if all its elements, so if and only if all its elements can be listed. Okay? All right, so let's do some examples. Okay, any questions about the definition? Do you understand this? All right, so for example, I guess number one, the set of positive odd integers. Let me say here, so the set of positive odd integers is countable, right? And why is this? Why is this set countable? That's actually what we just proved, right? We just proved that it has a cardinality as C plus. So number two, part A, show that the integers themselves are countable. Show that Z is countable. And here is a more surprising result. Show, and just to keep it simple, let's show that the positive rationals are countable. And then once we have that, we can extend this to all the rationals in general. Okay? I'm saying this is very surprising. Later on, we're gonna see why. Anyways, try to do this. So let's see. You already know how to do A, so do it, and then we'll talk about B. All right. How do we answer part A? What do we do to answer part A? All you have to do is, just read what's in red. What does it say? It says countable if and only if we can list the element. So don't kill yourself with a function. Just list the elements. How can we list the elements? You're missing something in your list. The list has to have all the elements. So what do we do? So what should be our first element? 0. Let's start with 0, and then we keep on padding. 1, -1, 2, -2, 3, -3, and so on. Does everyone understand this? So as long as you can list the elements, you're good to go. So solution for number 2, part A, well, look, Z, we can write it as 0, 1, -1, 2, -2, 3, -3, and so on. So this is a list of all the elements of Z. And that's it. Therefore, Z is countable. In other words, it means that its cardinality is the same as the cardinality of the positive integer. By writing this, you are implicitly giving me a bijection, a one-to-one correspondence with the integers, with the positive integers. Do you understand this? This will be the image of 1, the image of 2, the image of 3, and so on. The position is will be the input, the element in the domain. Okay, the position. Questions? Now, and alternatively, and I'll give this for you as a homework. But alternative, produce a function, produce a bijection. In this case, if you think about it a little bit, you can do it. For example, we can produce a bijection from the positive integers to all the integers as follows. We can define it like this. F of n is going to be, let's see, if n is odd, then I can do n plus 1 over 2. Okay? So by doing this, I'm going to capture, let me do n minus 1. That way I capture 0. So I can do n minus 1 over 2. So by doing this, every time that n is odd, I use this formula. So let's say when it's 1, I'm going to get 0. When it's 3, I'm going to get 1. When it's 5, I'm going to get 2, and so on. So this is going to capture all the positive version of 0, okay, including the 0. And then I only use the odd guys. Now when n is even, I'm going to use the even to cover all the negative integers. How? Divide n by 2 and put it negative. So when n is equal to 2, I'm going to get negative 1. 4, negative 2. 6, negative 3, and so on. Okay? Now, what you need to do once you define this is you need to argue that this function is 1 to 1 and that is on. Okay? That's homework for you. So homework, show that f is a bijection. So if you refuse to use the list approach, this is the kind of thing that you need to do. First, you have to come up with a function. Second, you need to argue. That's a bijection. Okay? So, it's up to you. You have your alternative there. Okay. Questions about part A? All right. So let's do. Let's see, because so far our listing has been straightforward. Now, how about the rationals? How can we list the rationals? Rational, you know what the rationals are, right? It's all possible fractions, right? All possible quotients with top and bottom are integers. Because it's positive rationals, then we are only looking at positive fractions, okay? So top and bottom are positive. Okay, how do we do this? Any ideas? I mean, we don't have much time, so I just want to show you. So for part B, here is what we can do. And this trick, we're going to use it later for something else, okay? So once again, notice that Q plus, this is all numbers of the form n over m, such that n and m are both positive integers, well, non-negative integers, and of course m cannot be 0. Okay? No, sorry, 0 is not there because I'm saying positive, so positive integers. Okay? So we need to somehow produce a list of this set. All right, here's what I'm gonna do. So I'm gonna make like a matrix. Okay, it's gonna be an infinite matrix. So I'm gonna have n here. I'm gonna have actually I like it this way. I'm gonna have n here. I'm gonna have m here. So in other words, m is 1, could be 1, could be 2, could be 3, 4, 5, 6, and so on. Yes, and then n could be 1, could be 2, could be 3, could be 4, 5, 6, and so on. Okay? So now here's what I'm gonna do. The first row, this is gonna be an infinite matrix what I'm about to write. Okay? The first entry, I'm gonna define how to do each row. The first row is gonna be n over n. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. So all fractions with 1 on top. Do you understand this? That's the first row. So it would be 1 over 1, 1 over 2, 1 over 3, 1 over 5, 1 over 6, and so on. So this first row is going to have all fractions with 1 on top. Do you understand this? Now the second row is going to be all fractions with 2 on top, and so on and so forth. Okay? So 2 over 1, 2 over 2, 2 over 3, etc. And so on. Okay? So all fractions with 3 on top. I think I probably don't have to. I'm gonna do the 4 and then etc. So 4 over 1, 4 over 2, all fractions with 4 on top. And this is gonna continue this way. and so on. Okay, so this continuous way, it's gonna be an infinite array of numbers. Everybody okay with this? A square array of numbers, which is what we call a matrix, an infinite matrix, going everywhere. Okay, so first of all, before we continue, do you agree that every single positive rational number is in this list? Give me a rational number, n over n. What do? I go down to n, and then I move this way up to n, and you find your number in this list. Does that make sense? So every rational number is here. Now, of course, there are a bunch of repetitions. For example, all of this diagonal represents the number 1. Okay? There's a lot of repetition, but that's fine. Now, this is not a list. Okay? I need to tell you how to produce a list. This is just a setup. Now, the trick here is how do we go through this list? How do we go through this to list all the elements? So I cannot just start from the first row and when I'm done go to a second one because we'll never be done, right? It's an infinity. Each row here is infinity. So what we're gonna do is the following. I'm gonna start with this first guy. Okay? So here is what I'm gonna do. I'm gonna then go down. I'm gonna pick this guy, and then I'm gonna go up and pick this guy. So let me start constructing my list. So basically, I'm gonna be moving the list. Okay? So that way we're gonna travel the list this way. Okay? So the list will be as follows. Again, there are many ways to traverse. This is just one. So I'm gonna start with 1. Then I'm gonna go down to 2 over 1. Then I'm gonna come back up to 1/2. And then of course, and then here's what I do. Then I go to the next one. And I will only pick a number if it was not on my list. Okay? Already. So 1 over 3, that's new. So I add it. Now I come back down. Should I pick this one? No, because we already have it in the list. Should I pick this one? Yes, it's a new one. So let's throw it in. Right? And then go here. This is a new one. And now come back up. Should I pick this one? That's new, right? That's not on the list. Then should I pick this one? Yes, we do. That's new. And then this one, we also pick it. It's 1 over 4. You know, go to the next one and repeat. Pick this one. It's 1 over 5. Now notice that here, this one I don't need to pick it. Why? Because that's 1/2. We already have it. Yes? This one, we don't need to pick it. That's 1. We already have it. This one, we don't need to pick it. That's 2. We already have it. Now, this one is a new one, which is, would be 5 over 1. And so on. Now, if I write this only, this is meaningless. If I only write this, it's not clear for people what comes next. Okay? However, if I pair this list that you're seeing here with this picture, hopefully at this point a pattern has been established. You should know that here's my 5 over 1, then what's the next thing to do? To the next one, and then go back up in the diagonal, the next one, come back down, and then down, up, down. So this way, we are traveling like this. And every time, we are covering more and more. Do you understand this? Do you agree that this will cover every single number here eventually? So our list will have every possible rational. So again, this is not straightforward listing, but understand that that's life. Okay, not everything is straightforward. Yes.
Why can't you just have the matrix? I feel like that should be enough to satisfy the list. Like if you can clarify that matrix serves as a list, isn't that valid?
Yeah, but to clarify that serves as a list, you should be able to tell me what's the 1000th element. Right? Remember, when you have a list, you guys, most of you are going to be programmed, right? What do you like to do when you have a list? Give me the 1000th element, or give me the 20th element in your list. So you need to have a predetermined notion of what this is, right? So if I give you this, it's not really clear what the 20th element is. Let's not just say 1000. What's the second element? I know. Okay, you could tell me, the first one is the one in the corner. Okay, good. What's the second element? Is it this one, like here? Or maybe you could have done it, first go here and then down. So it could have been this one. Right? And there are many other weird ways that you could do in here. Okay. So, but yeah, you have to somehow produce this. So this picture with this is enough because it kind of shows how to, or you could write a paragraph explaining this. Now, the English there will get in the way probably, and it will be very difficult to explain in words what we're doing here. A picture sometimes is worth 1,000 words. Okay? If you try to write a paragraph here, it may not be that straightforward. Okay, are we good with this? All right. So next time we're gonna see how to tell whether a set is uncountable or not. This is for countable. Now, are there uncountable sets? To argue that a set is not countable, what do you need to do? You need to somehow argue that it cannot be listed, that you cannot produce a list. It's not that straightforward. Okay? So we're gonna learn a technique called Cantor's diagonal argument that will help us do this. Okay? All right. So